This will be presented by Neil Brown, and the topic is RAID is more than parity and mirrors. Apparently not being the adventurous type, Neil's first job was at the university he graduated from, that's UNSW, maintaining the Unix computers, that is the level 7 from Bell Labs that he'd been taught on from the kernel on upwards. He had worked on various forms of Unices, making kernel hacking less of an option, moved into what appears to be more of systems administration work, and then came into an encounter with more Linux and more kernel hacking. Since then, he'd maintained the NFS server, now handed on to others, and MD RAID in Linux. Can we please give a very warm welcome to Neil Brown?
Yes, so I'm the MD RAID, software RAID maintainer in Linux, and I first started sometime around 2000 or 2001. I guess it was 2000-ish. Because I remember the 2001 linuxconf2013 in Sydney was when 2.4 came out, and in 2.4 was the first time in mainline Linux we had MD RAID, RAID 1, RAID 5 actually working. So I guess it was 12 years ago now. What's happened since? I seem to have been working on it ever since. After a while I transferred from uni to SUSE, and they paid me to keep working on it, and NFS in the meantime. But so what I want to talk about is what has 10 years added to RAID, to software RAID. I mean, we had the basic stuff a long time ago. What have we got now? Oh, hang on. It's just slow, isn't it? There we go. So RAID is for solving problems. I really wanted to focus on aspect of solving problems, and first identifying a problem and then solving it. Occasionally get people sort of sending emails and saying stuff, we could do this really cool thing in RAID, we could add checksums to every block. And maybe we could, you know, the RAID 6 parity calculation, you can, if one block is wrong, you can work out which block, and so we really should work out which block. And my response is, well, this is a cool technology, but what's the problem you're trying to solve, and is this the best way to solve the problem? And often it's not clear that doing these things actually is the best way to solve whatever problem they hypothetically think might exist. So I'm particularly, I follow the Linux RAID mailing list very closely, and I'm looking out for what are the common problems that people keep having, and that's where I want to focus my attention. I want to fix problems that people are actually having. So RAID is always about the original problems for RAID. You know, my disk is too slow. My disk is too small, and so we use RAID 0 to make small disks bigger, and also to some extent to make slow disks faster. Or my disk might die. My disk drive might just stop working one day. The blue smoke might get out, or somebody might pull the cable or whatever. And to solve those problems, I mean, I'm sure you're well aware we have things like RAID 1, which doesn't increase the size, but does increase the reliability. RAID 5, which does a bit of both, but tends to slow it down a lot. And RAID 10, what MD calls RAID 10, can have any number of devices, and you can see it's mirrored, and then the mirrored pairs are just striped however it works, so that's a 3-disk RAID 10. And that's kind of the basic technology. If any disk fails, it's taken out of the array, and in most cases you can still restore all your data and keep writing out, hopefully fairly well understood technology. And not one I'm going into anymore. But over the years there have been new problems, and I was thinking, these are kind of like first world problems, aren't they? My disk drive is too big, my disk drive is too clever, my disk drive is too fast, and I need more flexibility. So I actually want to talk about those 4 problems and how they subdivide, and what we've done in MD. But for the most part what we've done, to some extent what we might yet do. So in the first instance, my disk is too big, and resync takes too long. My machine crashed, as happens occasionally with Linux, and it was busy writing at the time, so we don't exactly know if it's still in sync. It comes up and we need to resync things. And when I started building MD arrays back in 2000-ish, I can't remember if we had 9 gig hard drives or 18 gig hard drives. It was about that sort of size. These days, as you know, you can get 3 terabytes without too much difficulty. And so this is a large increase in size, and they've got faster. I think maybe about 10 times as fast, if I sort of remember properly. So we're seeing maybe a 20, 30 factor of how long it takes to resync an array. Hours have literally become days. Waiting a couple of hours for a resync is boring. Waiting a few days is really tedious. And yeah, since it's about 2005, we got this code for adding right intent bitmaps. This was contributed by someone else who had a slightly different, I mean, they had a particular problem, a particular focus, which was having remote RAID 1. They wanted to have some storage locally and some storage on another site and keep them mostly in sync as much as possible. But they realised that there's a lot of latency and it's kind of slower getting to this remote site. So they wanted to make sure when the need to be a sync would be as quick as possible. If the connection broke and then was remade, they could recover without having to redo everything. And so you just store a bitmap in somewhere on the disk, or their actual original implementation stored the bitmap somewhere else altogether. On a separate, probably on a local disk. So it was a fairly asymmetric RAID 1, but that's not a problem. So it's a bitmap, 1 bit for every block. How big is a block? Well, his focus was let's have really small blocks because the latency was a big problem. And it doesn't actually work for 512 byte blocks for various reasons, so that was his target. But anything from 1 page upwards. So his focus in writing this was really small blocks to cope with remote RAID 1. But it's very useful for the rest of us who have both our disks really close together and they're both of an equal speed. We tend to use much bigger, so 1 bit responds to a somewhat bigger chunk when you're building your own RAID in your disk. But it does mean that resync, if you've got a bitmap, right intent bitmap on your RAID, resync will probably take, I don't know, maybe minutes. Certainly not hours or days if you choose the chunk size properly, and it depends a bit on some various parameters, but it would typically be minutes, which is much better. It's a concept that's also even used for off-site backups to some extent, because people will have 2 disks, and so it's a bit like the remote RAID 1 concept, except the second disk is physically moved. You bring it in, you plug it in, it rebuilds, you take it away, and while you've taken it away, bits get added to the bitmap as things are changed, but never deleted because the array is degraded. When eventually the disk drive is brought back in and plugged in, the recovery will just update those missing blocks. Anyway, it means that the big disks won't cause a problem for resync anymore if you turn on the bitmap. So it's a small cost in turning on the bitmap. Writes have to update the bitmap and then write the data, but in most cases it's quite an affordable cost. It doesn't actually solve the initial sync. I mentioned the initial sync for RAID 5 because you don't really need an initial sync for RAID 6 and RAID 1, various reasons. You do for RAID 5 because RAID 5 does a read, modify, write, so because it does a read, the initial parity must be correct. There might be other ways to solve that we'll come across later. Part 2 of my disk drive is too big. Well, first resync takes too long, now recovery takes too long. So it's important to understand the difference between that. Resync is after a crash or unclean shutdown. You expect it's mostly in sync, but you don't know for sure, so you have to copy things around. Recovery is 1 disk died, was pulled out, has to be replaced, so you recover onto that disk. I mean, if the whole device has died, there's really not a lot that can be done. There's maybe a tiny thing that might help sometimes, we'll get to later, but really there's not much you can do. You can't, so once it's died, there's not much you can do, but often you know before it's going to die. And if the recovery all happens before the disk dies, then the cost is much less. The array is degraded for much less time. As this is a relatively new feature we just got in the past year, which I call hot replace. And so it means that an array has several different slots. In the pictures earlier, each array had 3 slots with 1 drive in each slot. Now you can actually have 2 slots, two drives in each slot, the original and a replacement. And so once you put the replacement drive in, you can run a recovery process and they'll copy all the data onto the second drive, usually copying it from the original drive onto the the replacement drive. However, if the original drive's got a bad block or something, it'll get the data from somewhere else, from one of the other drives, and write it there. So you can do the recovery before removing the bad drive. And so while it doesn't take less time, it does mean there is less time when the array is degraded. Hopefully pretty much 0 time when the array is degraded if you get your warnings early enough, if you have a drive spare on hand, stuff like that. And that will, in the latest kernel, that should happen automatically. As soon as you get any write error, if there's a spare, it won't evict the failed drive. It'll kind of leave it there if you got bad block logs. So yeah, you need the configuration right. I'll talk a bit more about that later. But it'll just automatically start rebuilding to a spare if it's got one. So this allows recovery to happen before the failure, which is by far the best time for it to happen. And also is particularly helpful if you've got an array and it's got some bad blocks that you don't know about it. Often, if you try and do a recovery, you find these bad blocks during recovery, and recovery can't cope so well. If you're doing a hot replace, if there's a few bad blocks on a device and you decide to replace it, and you start replacing it, and you find another bad block on another device, you would previously, that's throw up hands, can't cope. But if there's another bad block on that device, but the device you're failing is actually, that block is okay there, then you can keep going, you survive. So you can go all the way through and finish the recovery completely. Question at the back?
Which kernel does that start with?
Which kernel does that start with? What's the current kernel? 2.8.2. Is
3.8 RC5.
Okay, so it's in 3.7. I wouldn't promise it's in 3.6. It's about that sort of time frame. In terms of that mdatom command, that's only in the Git version of mdatom. I haven't actually done a release sufficiently recently of mdatom to have that command available. But people have actually, in the mailing list I send instructions how to poke numbers into a Sisyphus to make it happen, and people have tried this and it has worked.
Have you optimised that replace in any way by basically doing an image copy of the bad drive and then doing it onto the new one with bits that miss you can't copy, but then doing resync rather than having to read and copy and so on? Basically do a sequential copy of the drive onto the new one and then recover the new one with all the bits that you couldn't copy.
Well, that's essentially what it does.
Could you summarise the question for? Yep.
Yeah, when it's doing the recovery to a replaced drive, it basically, while it's doing that, it's reading the original and writing to the replacement, because the best way to get, quickest place to get the original data from is from the original drive, for the most part. When it hits an error reading from the original drive, it'll go and get it from wherever else it is and write that block, and then go back to continuous streaming from the original drive while they're a good block. So it basically does, copies the whole uncertain drive to the good drive, and if there are any problems, it gets it from elsewhere in the middle. Is that kind of that?
So rather than a typical rebuild or recovery where it's got to read,
yes, exactly. So it doesn't read all the disks and recalculate the missing block if it can avoid doing that. So recovery takes too long, so the best time to do it is a bit earlier. Third problem with my disk doing too big is errors per disk seems to be increasing. You can maybe argue this based on the fact that the error rate per block is probably, the reliability per block is probably increasing. The disk drive makers are probably getting clever, so the error rate per block is going down a bit, I'd expect. But the total number of blocks on a disk is going up significantly, as you can imagine. So the errors per disk is probably going up. And the evidence is from reports on the mailing that that's probably the case, that people more and more are getting 1 or 2 bad blocks here and there, or 3 or 4 bad blocks here and there. Without the drive doesn't fail completely, but you get this collection of bad blocks. And that's happening more and more often. So individual bad blocks on one device is more likely, individual bad blocks on multiple devices is becoming more likely too. So if we still have redundancy, if we find a bad block, we really want to not throw out the drive. I mean, the original RAID would just throw out the drive, rebuild onto a spare, maybe take an hour if it's a really big drive, all done. We don't want to do that. So what we if possible, we recover just the one block. And we've been doing that for what, since 2006, so that's 6-7 years. And this works because modern drives are fairly clever under the hood. You know, they'll remap where the media is really bad, they'll remap it. If the media is not really bad, they'll be able to rewrite it. So that we're working with the drives, sort of knowing how the drives tend to behave and trying to get MD to fit in with that. And so quite often MD will find a bad block, get it from somewhere else, write it out, everything's smooth and keep going again. But what if the array is degraded when this happens? If you do actually have a drive lose its smoke and have to do a rebuild from scratch, you're reading along and you hit a bad block. Again, you don't want to discard the whole array. I mean, maybe there's this one block, maybe there's even this one stripe that you can't read, but losing, you know, one 4K, 8K, 64K block in 3 terabytes is maybe not the end of the world. So we want to be able to just fail the block rather than failing the whole device. And to do that, we recently, I think in the middle of the year, a little bit before the drive replacement anyways, maybe early in the year, last year, we gained bad block lists. A bad block list is simply a list stored in one block towards the end of the device, and maybe I should be storing it in 2 different places. But at the moment, sort of small steps, we're storing it in just one place. So we're storing a list that it currently can contain up to 512 regions of the disk, where a region is 1 or 2 or 3 few adjacent blocks. And so we know we can record that this block is bad. And that's particularly useful because it means we can record the block is bad even if the media isn't bad. So that when you're doing a recovery, you hit a bad block, you want to copy this is a bad block. You don't want to actually, found a bad block, I'll write zeros there. That would be a bad thing to do because when the application comes to read that block, it might get zeros and hey, thinks it's good data. What you want it to do is read the block, get an error, and deal with the error however it is that errors need to be dealt with in that circumstance. So you need to actually copy the concept of a bad block, and having a bad block list allows us to do that. And yeah, bad block lists also, I think, when you're reading, hang on. No, yeah, so yeah, bad block lists allow us to. So those are the 3 things. The 3 subsections of my disk is too big is, things take too long and there are too many errors. What about my disk is too clever? It retries too much and retries and retries and retries, and I don't want it to keep retrying like that. Some disks you probably know have time limited error recovery, TLER or something, so it doesn't retry for so long. But sometimes you do actually want it to retry. I mean, if you've got a RAID 1 array and it's optimal and you get a read error on one drive, you want to abort that and read from the other drive and then maybe try and write it back to the first drive and sort of sort that out in the background. But you want to abort it quickly. If you've got a degraded RAID 1 array and you get you want actually to retry that a little bit harder, as hard as it can, really. So it's not a case that you can just, some sort of drives, you want a RAID style drive and a RAID array and a non-RAID style drive and not a RAID array, because the status of whether it's really in a RAID or not is a dynamic concept. It changes due to failure. So we've got this fail-fast flag. We've got 3 fail-fast flags in Linux, which is really cool. Used to have only 1, now we've got 3. They're not really used very much, and they're not really documented at all. And I tried quite some years ago when there was just the 1 flag, I tried sort of getting RAID to set it and drives, SCSI drives, I think, no, SATA, whatever drives I had at the time, I think they were SATA drives, they just kind of drop out of the array really quickly. It's like if you say fail fast, they would really fail fast. And I thought, well, am I using it wrong? But I don't know, because there's like almost no documentation. There's no documentation, very few use cases. I mean, if you look in the code, so we've now got the 3 flags, dev, transport, driver. So presumably fail fast dev tells the device to fail, transport tells the transport, the connection between you and device, and driver tells the driver to fail. So we don't get retries at the software level, I guess. So let's assume what it's meant. The only code that ever really sets dev is BTRFS. At one place it sets this flag. Why it sets that one and not the others, I'm not sure. The only code that ever sets the transport flag is multipath code, and that makes sense. I think multipath is probably the one place where this has actually really been tested and actually works. Both DM multipath and MD multipath, and just don't ever use MD multipath. No one cares about it, no one maintains it. Use DM multipath. It sets the flag, and so it knows when a path is. So if a path fails, it can fail quickly, and there's no retry, and that's all good. There is, I mean, I tell a lie now because there is one place, essentially one place where all 3 flags are set, and this is, if I read the code properly, in some part of the SCSI drive where it's sending test unit ready, TUR? Yeah, test unit ready command. So when it sends a test unit ready commands, it sets all 3 of these. I'm not sure why. I didn't actually bother looking in the code to find out exactly what happens when you set these devices. There aren't that many lines of code, though, that actually pay any attention. So I'm not sure how useful these are. However, I have actually used them a bit because we have a client who had a particular bit of hardware that particularly wanted this sort of functionality from RAID, and so we, as in SUSE, kind of could control the whole stack, and for that particular drive and that hardware, we made sure that one of these flags did what we wanted, and that gave me a bit of experience in adding sort of fail fast code to RAID and thinking about the issues. And so SLES 11 SP2 or something does have a fail fast flag, and it does work on one particular bit of hardware, and we do support it for 1 or 2 particular customers. Probably support it for other people as well, but we wouldn't recommend it to them because I mean, it's a particular use case. It seems to work for that. It solves their problem, and that's all good. And it's given me some experience and some background and some thoughts. So I might actually be able to put this in a more general way in the upstream kernel and see if it works. But testing it is really hard because I've got software virtual devices that return errors at suitable times, which is nice. But getting a device that fails more quickly in certain circumstances is a bit more tricky, and actually knowing that it works in real hardware. It'd be good if I had some disk drives that failed in different interesting ways. At least I think it would be good. Question, Matthew?
So we put something into the NVM Express spec to allow you to scar particular sectors in the drive, and I was wondering if perhaps you could take advantage of that, because we did put it in thinking of you.
Oh, thank you. So what spec was...
Say he scarred you.
Sorry, what spec was this?
NVM Express.
NVM, so the NVM Express spec allows you to scar individual blocks, which causes, so that causes it just to give an immediate error message, or not a delayed sort of retry? So it's still, if there's any retrying in the driver, we could test for that. Yeah, okay.
You tell the device not to retry as well.
Tell the device not to retry, and it might be something worth exploring there. I did see something somewhere about somebody writing an error onto a drive for testing, but I haven't explored it any further. It's certainly something worth exploring though, yes. Yes, hard to test, no documentation. My drive is too clever, and my drive is too fast. This is more recently, this is really talking about my drive as an SSD, and you don't support them very well, but I thought saying my drive is too fast was a bit cleverer, so I did. First problem with my drive is too fast, and this is a problem that Jens Axbo has been sort of fixing really well in the block layer, is because the drive is so fast now, it's faster than our software, and we're starting to look bad. You know, each request to a spinning Rust takes milliseconds. Each request to an SSD, a good SSD, can take microseconds, and you start noticing the overhead of locks and of jumping between CPUs when you shouldn't do, and things like that. So we've done a bit of yeah, the block ALO is really good. You can actually deliver lots of requests per second, lots and lots of requests per second through the block layer, but MD doesn't look so good now, so we need to lift our game. So we did a bit of lock removal and batching, so we take the lock, do 16 things at a time instead of just doing one for every lock, and that's helped a bit. As you might know, RAID 5 and RAID 6 is kind of one thread that does all the parity calculation and handles all the requests, because it was a lot easier that way. We tried multi-threading that some time ago, and the performance went through the floor, probably because cache bouncing or stuff that I know about but don't really understand at a deep level. So we've actually got someone from Fusion.io, in fact, has contributed some multi-threading code that he claims works goodly. I haven't had a chance to look through it properly, but there's a good chance that'll help, at least in some circumstances, by being able to, if you've got multiple cores, which we all do these days, even in our phones, you know, you can actually do multiple XORs or multiple RAID 6 calculations at the same time and process the data more quickly. So that's getting there. Like, the latest kernel should be somewhat better on your SSDs. You've got enough SSDs to make a RAID, but there's still a bit of room for improvement.
Neil, have you tried using multiple RAM disks to back an MD device to do higher-ups testing on just a single machine? Because I think that makes a test to do a couple of million IOPS to a file testing to really stress the locking and whatnot.
Yeah.
And it's a really great way of actually saying, oh look, I've got a really fast SSD, because you can do a couple of million IOPS through 8 to 10 CPU cores.
Right. Yeah, it's a good idea. So the suggestion was to simulate, if I don't have enough SSDs myself, which I admit I don't, and donations are welcome, you can simulate them with RAM disks. Obviously, you need to keep them relatively small, but you still might be able to see how many IOPS per second. So certainly it might be a useful way to be testing the multi-threading code to see at least to see if it doesn't put the performance down, which is, I'm more concerned that it doesn't make the performance worse than that it does make it better. Hopefully it will. So the other thing with SSDs, this has really got nothing to do with how fast they are, is the need for trim, need for just to tell it it can erase blocks and forget about them. And if you think about it, with the things that aren't RAID, linear and RAID 0 are really not RAID because they're not redundant, but it's kind of trivial to implement trim for those. You just break the trim request up and send it down, and that's kind of not even interesting. For RAID 1 and RAID 10, the mirroring levels, it's mostly pretty straightforward. Again, you send the trim request down to both sides of both pairs of the mirror, and that's all good. But there's issues with resync. If you ever have to do a resync, you don't want to read from one drive and write to the other, because you just undo all the wonderful trimming value you got from trimming. And similarly with recover, if your drive fails and recovers, what do you do then? How can you write? Well, I mean, the options are you just write all the data out and then run some offline trimming thing to go back and retrim the whole file system, which you could do, but isn't really very elegant. So there's three options there. We could have another bitmap, a bitmap that records whether, so the idea is not a bitmap to say whether it's been trimmed or not, a bitmap to say whether we think this should be in sync or not. And then when you trim something, you say we don't care about this being in sync, because really we don't care about what data there is, so we don't care if it's in sync or not. So we'll never try and copy it. We should never try and even read it. But if it ever does get read, we can just immediately return zeros because it's not meant to be in sync. Having that means we could just set all of the bits at initial time, at initial array creation time, and the array would be in sync. It'd mean we'd then have to, every time we set a bit, we'd need to resync a little bit of the array, how that would perform is an interesting question. But also having that other bitmap there would help in the recovery case, It'd help recovery go a little bit faster too, because you only have to, if you've got that bitmap, then you only need to recover those bits of the array that you've actually ever written data to. So it's a little help there.
Sounds like you could make use of something like the DM thin provisioning algorithms to keep track of where you've actually had data written.
Yeah, it's kind of like...
It's a layer, like a thin layer over the top. You don't need any allocation or anything like that, but if you write data, you just mark that range and it's got data in it, and when a trim comes down, it comes down through thin P, and you punch that range out and you can throw the stuff down further.
Yeah, so it's comment is this, that sort of concept is very similar to thin provisioning, the new thin P stuff in DM, and maybe that would be the best approach, to forget about the whole idea of putting something in MD or putting too much intelligence in MD and just saying, well, if this is important to you, use DM thin on top. But yeah, there's issues there to be explored, and it's certainly an option worth exploring. Thanks. But if we didn't do that, if we just stayed with the array, I mean, if we didn't want to use a bitmap for whatever reason, maybe we could test for 0, because, I mean, we're currently only supporting trim on those devices that return 0 when you try and read a trimmed block. I mean, I don't know exactly what the specs demand, but I think my understanding is that...
I know what the specs demand.
And tell us, Matthew, what are the specs demand?
The specs, it varies between 3 different storage protocols I know about.
Should we get this man a microphone?
Like? So you... On?
Okay, so serial ATA, so ATA drives can return all zeros, all ones, random data, the data that you last wrote, but not data from somewhere else on the drive. SCSI is more, yeah, because we thought, oh yeah, that might be a security hole. Let's see, SCSI mandates returning all zeros.
Oh,
SCSI's got it sorted.
It depends on what SCSI command you use.
Oh, that's right.
Or write same.
You're right, it does.
If you write same, you can write any repeated data that you want to it, whereas you use unmap, it has to return zeros.
That's right. NVM Express is either all zeros, all ones, or the previous data that you wrote to it. And unlike serial ATA, it does require that it remain constant. Serial ATA actually allows the drive to change what it returns.
Yeah.
And the RAID people know how wonderful that is.
Yeah, the SARD protocol actually has a bit to say whether it's deterministic or not, so you know when the drive is going to lie to you.
And of course...
It's so much better.
I think that should be summarised.
I'm not quite sure how to summarise that. The answer seems to be that it's a mess, that different drives can do different things. And of course, as long as if a drive does something unpredictable, and my preference is just to say we don't support that there. If a drive does something predictable, we should be able to work with that. But of course, in RAID, you need all the drives to do the same predictable thing, or you're going to trip over yourself. So maybe there's a reason they haven't actually implemented anything here yet. I'm not really sure. And the other option is, you can avoid writing, during a resync, you can avoid writing too much. If you do read them both and compare, and if they're both all zeros or all ones or something, just move on. Maybe you could have done a trim, but at least you didn't write over trim data. So it's an option. I'd almost go for just do read compare all the time. RAID 10 currently does that, but it might slow people down sometime, and one doesn't like slowing people down. And for RAID 5 and 6, it's really hard. It was particularly hard until recently, all trims had to be power of 2 in size, and RAID 5 stripes often aren't. But I think that's been fixed.
That's been fixed, yeah.
Yeah.
The underlying devices can set any discard granularity or alignment that they require, and the higher layers must be able to follow that, or their alignment can be a superset of what the underlying devices can support. Yeah,
so as of fairly recently, the alignment and granularity don't have to be power of 2 anymore. They can be any size.
Yeah.
And the fourth point was I would need more flexibility. And people don't like planning ahead. I love microwave ovens because you can cook, don't have to plan dinner in ahead. I love the hole in the wall because I don't have to get cash out before the weekend. And I love being able to reshape my RAID arrays because it means I don't have to plan.
Except you can't reshape the file system on top.
Yeah, well, if the file system knows about the shape of the array and knows about where the stripes are and aligns itself with that, then it's a file system problem. So we can convert between RAID levels. Well, we can add drives to a RAID. Adding a drive to a RAID 1's easy. Adding a drive to a RAID 5 or 6 is kind of okay. We can move stuff around. Adding drive to a RAID 10, RAID 10 has many different options, so I think we support some of that now, but not all different combinations. Converting between RAID levels is fun too. I've just got a bit of a picture of that. The way I've abstracted it in RAID is converting between RAID levels has to happen instantly. So you can convert a 2-drive RAID 1 to a 2-drive RAID 5 just like that because they both have the same data everywhere. Converting a RAID 5 to a RAID 6, we convert it to an interesting, so this is a RAID 5, this is a RAID 6 where all the Q blocks are at the end with a very non-standard layout. Normally you rotate everything. But so this is defined in the code as RAID 6, and then we just change the layout block by block. We change the layout to put the Q blocks where they should be. And that can take a long time, but sometimes things are worth waiting for. And so there's a number of different conversion options. And people seem to like that. They seem to be able to like to change their mind or add an extra drive. And this works a lot better if you add a drive, if you add 2 drives. So if you add 1 drive, you're changing everything in place, which we'll be reminded in a moment, is problematic. If you're adding more, if you're making the array bigger, then except for the beginning bit, you're reading data from a different place to where you're writing data. You're sort of shuffling everything, you're spreading the data out, and so you can read a whole lot, then write a whole lot without worrying about writing on top of yourself. So that's a better thing to do if you ever want to if you want to reshape an array, resize it at the same time. But yeah, we can do that, and I've been able to do some of that for a while. But yeah, I want my reshape to finish today. And so when you're reshaping without resizing, basically what we have to do is read a stripe, write it to backup, rearrange the data and write it back, which is why we had the backup, because if we crash while we're writing it back, we've got corruption, we can't possibly recover from that. So we rearrange it and write it back, then we update the superblock header to say that, to tell it where we're up to, and then we can forget about the backup and write some more data to the backup, and that's just really slow. It works, it seems to be reliable, my self-tests say good, but it's slow. So what we can, this currently works at RAID 10 because we have a customer who is using RAID 10 and wanted this, but the kernel code's there for RAID 5 as well. The idea is, and MD-Atom now will always put this big buffer at the top of your array if it can. And so what happens if you're reshaping this 4 drives into that 4 drives, it reads from there and writes to there without having to back it up anywhere. And then it updates the superblock and reads from there and writes to there. Hopefully it does it more than 1 stripe at a time. Hopefully it does about a megabyte at a time or so. That's about, I can't remember how much I reserve, but it's the order of a few megabytes. So that should significantly improve the speed for some of the really slower reshapes.
Can you then only do it once? Because you've lost your... But the buffer should be at the bottom now.
Yeah. Well, there'll be a buffer at the bottom, and you see the next slide. But I think I sort of aim to use about half the buffer to allow for that. Every time you use half and then half again. But yeah, you can move it the other way. People want to oh dear, I didn't really want to reshape that. I want to abort that reshape. If you can't currently do it at the moment, once you started, you've got to go all the way to the end. But it's kind of the code is actually there in the kernel to be able to do it. MD-Atom just doesn't know how to do it. So yeah, reshaping in both directions. I mean, when you're changing the size, when you're making an array bigger, you've got to kind of reshape from the beginning to the end. When you're making an array smaller, you've got to reshape from the end to the beginning. When you're just changing an array in place, you can go in either direction, and the kernel does know about that, but MD-Atom doesn't use it at all, and it needs, obviously, to be tested a lot. And that would actually allow you to reshape, to move the offset, the data offset around. You can also change the chunk size by doing that, because can't guess. And the other bit of flexibility is people like to be able to boot some other OS that doesn't understand MD's metadata formats. We've got a couple of different other metadata formats we can understand. DDF2, which I'm not sure that anybody, well, the people must, Dell's sort of, the magic number, you know, the first 2 bytes of the super block of DDF2 are 11DE, Dell. So I think that's where that format came from, though HP seem to be interested in it as well a bit, but I don't hear much about it. Intel's Matrix Storage Manager, IMSM, Intel are very active, have been really pushing the development of that, and they've got that pretty much completely supported. So you can have your software RAID array that works fine with Linux or with Windows, and it can be reshaped. You can start the reshape in Linux and finish the reshape in Windows. At least I've never tried that myself. But they tell me that that should work, and there's no reason in principle why it shouldn't work. It's the same kind of people reading the same specs, writing the code, testing it against each other. It requires this user space monitoring program, MDMon, to manage the metadata that some people feel uncomfortable about, that I think is the right solution. And as long as you can convince systemd not to kill it at the wrong time, which we can do, it's all good. So it's about problems, and there might be future problems. We might need more than just 2 blocks of redundancy one day. There's different schools of thought. I'm not totally convinced, but I'm not at all against it exactly. There might be new hardware one day, probably tomorrow, yesterday. But the other question is maybe smart file systems like BDRS will make it all obsolete and I can go off and play with my phone instead. Or take photos of cats. So yeah, that's what's been happening in the last 10 years with RAID. It's not just parity and mirrors, it's all sorts of other things to try and fix other problems that come up in the meantime. Thank you for listening. Any questions or comments?
Thank you, Neil Brown. We do have time for a couple of questions. I can see one hand there and one hand up there.
So not so much a question, but you've got questions there that you're asking us.
Yeah.
Okay, so will smart file systems make RAID obsolete? That's probably the one that most people care about because ButterFS is going to be the next big thing.
It already is, isn't it?
It's going to be the next big thing for the next 5 years, the way it's going. But seriously, when you start talking about enterprise distributions and so on, smart file systems are not going to replace our current file systems anytime soon. RAID is not going to be obsolete for the next 10 years because people are still going to be running it and still going to be needing it because the smart file systems can't do everything that the existing file systems do well. There's a trade-off. So I don't see that RAID is going to be obsolete anytime soon. Yeah. So put your phone away now.
All right, there's a hand there and a hand there and a hand there. So
This will be snarky today for a second.
With the was it the checksumming of RAID 5? Can you retroactively apply that? What was the checksum of the? If you can go back a few slides, I'm sorry, I've forgotten the word you used.
I can't think what you're talking about. Is it too fast? Or
Was the bitmaps? Shit. Sorry. No, because you're adding extra checks to the RAID 5 data on disk.
No.
RAID 5 to RAID 6 conversion.
Converting it to RAID 6?
Man, sorry, I just had a brain fart.
Oh well.
And also the changes that have been done to RAID 5, can they be retroactively applied, or do you have to basically recreate the array?
Oh, okay, so that's a good question. So the important thing is when we make changes to metadata, so we've added a bad blocks list, can you add a bad blocks list to a live array? The answer is yes, if there's some space there. We don't always reserve enough space, and your MD-Atom will always reserve enough space. But given that you can resize, you can make an array smaller, you can now move the offset. So if you really wanted to, you could reshape the array so there's room near the metadata for a bad block list. Yes, you could move the offset down you'd have to shrink the array by a few megabytes, move the offset down, and then you've got an offset at the top to do reshaping. So to the greatest extent that it's possible, yes, but well, just don't think about it, just write commands. Matthew.
The question's more for Dave, actually. Are you saying that XFS is not going to be integrating RAID support all on its own?
No, RAID is a function of the hardware.
Sorry, I'm going to have to cut it because we do have to leave this evening.
We do.
So I hope you guys enjoyed the talk.
Once again, thank you very much, Neil.
Thank you.
We do have a little something from LCA 2013. Thank you very much.